Cool. So we're continuing on from the inversion method stuff last time we looked. So looking at transforming between distributions. So in describing the inversion method, we introduce a technique that generates samples according to some distribution by transforming the canonical uniform random variable in a particular manner. So it's remapping that uniform variable to other distributions. Looking at a more general question here, which is the distribution of results when we transform samples from an arbitrary distribution to some other distribution with a function f. Understanding the effect of how such transformations is useful for a few reasons, though here we will focus on how they allow us to derive multidimensional sampling algorithms. Suppose we're given a random variable x drawn from some PDF p of x with the CDF of big P of x. Given a function f of x with y equals f of x, we can compute big Y equals f of big X. It's the individual sample, I guess. We'd like to find the distribution of the new random variable y, okay, based on some remapping. In this case, the function f of x must be one-to-one transformation. Multiple values of x mapped to the same y value, then it would be impossible to unambiguously describe the probability density of a particular y value. A direct consequence of f being one-to-one is that its derivative must either be strictly greater than 0 or strictly less than 0, which implies that for a given x, probability of that remapped value being less than the function value is equal to the probability of the original random variable being less than the input. Am I parsing that right? Seems like it's okay. So it's kind of like if you're halfway through the distribution, then you're kind of halfway through the distribution kind of idea. Is that kind of idea? That's kind of my interpretation.
Sounds right to me, but
I'm maybe guessing a little bit. From the definition of the CDF, we can see that PF of y is PF of f of x. Again, what PF is.
PF is the CDF of the mapped distribution.
Okay.
And the original P is the original CDF.
Okay. This relationship between CDFs leads directly to the relationship between their PDFs. If we assume that f's derivative is greater than 0, differentiation gives this that p of x or pf of y is times the derivative with respect to that function. With respect to x, I guess. So p of x I guess I'm not exactly parsing what's going on here, but
It's the differentiation of the above equation. So we have CDF, right? PFY equal to PX. And then when we differentiate that, because we want to differentiate according to x and y is fx, so we get the below
okay.
df divided by dx.
Okay, so in general, if f's derivative is either strictly positive or strictly negative, and the relationship between the densities is that pf of y is the I guess integral of or no, it's not integral. So inverse something inverse. Absolute value. Okay. Guess that's one way to. Yeah. Anyway, how can we use this formula? Suppose that p of x equals 2x over the domain 0 to 1, and let f of x equals sine of x. What is the PDF of the random variable y equals f of x? F of x. Because we know that the derivative equals cosine of x. We can write it this way. So it's p of x over cosine of x. The absolute value of cosine of x is 2x over cosine of x. I can rewrite that with an identity, I guess. Something along those lines. This procedure may seem backward. Usually we have some PDF that we want the sample from, not a given transformation. For example, might have x drawn from some p of x and would like to compute y from some distribution pf of y. What transformation should we use? All we need is the CDF for the CDFs to be equal, or pf of y equals p of x, which immediately gives the transform f of x is the inverse of the transform time applied to the transform of x. As generalization of the inversion method, since if x were uniformly distributed over 0 to 1, then px of x and px of x equals x, and we have the same procedure as we introduced previously. Um, so I guess if you've got that transform and then some inverse transform, then you get your original values back or something along these lines. Sorry, I'm pretty tired tonight. Not really parsing this super well. All right, so we got transform in multiple dimensions. The general d-dimensional case, similar derivation gives the analogous relationship between different densities. Not sure the derivation here. It follows the same form as the 1D case. Suppose we have a d-dimensional random variable x with density function p of x. Now we let y equal t of x, where t is a bijection. In this case, the densities are related by pt of y is equal to pt of t of x. Probably one.
Bijection
Okay,
just
it's the one-to-one thing that they were talking about before, I guess.
yeah.
Okay, so that's same as what they were saying before, I guess. Okay.
Yeah, it's the same way as before. And Jacobian matrix, I think we talked about this before because we read a chapter in like PBRT V3, and yeah, Jacobian is basically derivative in multi-dimension.
Okay. Huh. So interesting. It's like with respect to the different dimensions. With subscripts index dimensions of t of x and x. Okay. So for a 2D example of the, we use this equation. Polar transform relates Cartesian xy coordinates to a polar radius and angle. Suppose we want to draw samples from some density p of r and theta. What is the corresponding density p of xy? The Jacobian of this transformation is that matrix applied to, yeah, and we can evaluate that to get these different values. for the Jacobian there. The determinant of this is r times cosine squared of theta plus sine squared of theta, which is, you can replace stuff in the parentheses with 1, so it's just r. And okay, the probability distribution of p of x of y is then p of r theta divided by r. Okay. Of course, this is backward from what we usually want. Typically, we start with a sampling strategy in Cartesian coordinates and want to transform back to one in polar coordinates. In that case, p of r theta is equal to r times p of xy. In 3D, given the spherical coordinate representations of directions, equation 3.7, the Jacobian of this transform has a determinant absolute value of jt, or determinant of jt is r squared sine theta. So the corresponding density function is p of r theta phi equals r squared sine theta p of xyz. Okay. Transformation is important since it helps us represent directions as points on the unit sphere. Sampling with multidimensional transformations. Suppose we have a 2D joint density function, p of xy, that we wish to draw samples x, y from. Their densities are independent, and they can be expressed as the product of 1D densities. So p of xy is px of x and py of y multiplied. So random variables x, y can be found independently, sampling x from p of x and y from p of y. Px and py. Many useful densities are not separable, however, so we will introduce the theory of how to sample from multidimensional distributions in the general case. Given a 2D density function, the marginal density function p of x is obtained by integrating out one of the dimensions. Okay, so integrating with respect to y to get the p of x from p of xy. It's going to be thought as the density function for x alone. More precisely, it's the average density for a particular x over all possible y values. So that's a okay. So p of x is then the probability distribution function of x, and get that by taking the integral with respect to y, I guess. If we can draw a sample x from p of x, then using equation 2.1, we can see that in order to sample y, we need to sample from conditional probability density y from p of y bar x. I'm not sure what.
Conditional probability.
Oh, okay, sure.
So it's like y, y if we know x.
Okay. Okay, cool. And that's given by this. So that's p of xy over that result from before. That's the p of x. P of y given x is okay. Sampling from higher dimensional distributions can be performed in a similar fashion, integrating out all but one of the dimensions, sampling that one, and then applying the same technique to all the remaining conditional distributions, which has one fewer dimension. So they have sampling the bilinear function. So that's f of xy is this equation with these these different so W0, 1, 2, or 1, 2, 3, I guess, are two-dimensional points, looks like. After integration and normalization, find the PDF is for f of xy over the sum of those points. Okay, right. Okay. The four corners, between the four corners there. That 0 to 1 distribution. That's okay. So two-dimensional point. Okay, so that's the PDF. So two dimensions of this function are not independent. So sampling method samples a marginal distribution before sampling the resulting conditional distribution. Okay. Sample a y, and then I guess there's a which argument is the mixed term on their lerp? Is it? Yeah, okay, the first term is. Okay, so you're mixing with p of x, or p of y rather. Um, uh, so mix between W0 and W2 is the variation on the y-axis, then something, and then the between 1 and 3 is also that. Okay, so this is the y coordinate changes. We choose either x or y to be the marginal distribution. If we choose y and integrate out the x, we find that p of x is the integral from 0 to 1, or 0 to 1 of p of x dx. So we get that. So p of y performs linear interpolation between two constant values. We use sample linear to sample from the simplified proportional function since it normalizes the associated PDF. Applying this 2.1 again, canceling out the common factors. Get this. So we can also sample that with x using the same function there. Because the bilinear sampling routine is based on the composition of two 1D linear sampling operations, it can be inverted by applying the inverses of those two operations in reverse order. Okay, so I guess that's a way to do the inverse transform. I didn't see if there was questions. Yeah, the bilinear section. Yeah, I should probably yeah as well.
Should we end the recording?
Yeah, right.